My name is Neil Patwari, and this is EC 5510 Random Processes. This topic is on the Poisson process, and specifically how to derive the Poisson process from a Bernoulli random process. Okay, so a Poisson process is continuous arrivals in time. So packets arriving at a router, they can arrive at any real valued time. And they're going to arrive at some rate, some average rate that's constant over time. So let's say that lambda packets arrive every second on average. And so what we're going to do is we're going to take two steps. We're going to sum the number of successes in a Bernoulli random process that approximates this, and then we're going to let the block size go to 0 so that the approximation becomes a success. So let's look at step 1. Okay, so step 1. We're going to divide this time from 0 to t into blocks. Let's divide it into equal sized blocks. Here I've got 1, 2, 3, 4, 5, 6 blocks between 0 and t. What I'm going to do is, in a Bernoulli process, is I'm going to make it a 1 if there was an arrival in that time window. So here, the first block, there was an arrival. Second block, an arrival. Third block, there were 2 arrivals. But with the Bernoulli random process, I can only indicate 1 or 0. So here there was an arrival, here there was an arrival, here there was an arrival, and the final block there was no arrival. So what do I get? If I were to put this Bernoulli random process into a summer so that I get the binomial counting random process, I would have 1, 2, 3, 4, 5 instead of 6, which is the actual total number of arrivals. That's why we're going to do step number 2. We're going to let the block duration go to 0 so that if I have smaller and smaller blocks, I'll have blocks that are small enough so that there's only 1 arrival in every block, and eventually that sum will become exact. Okay, so let's look at what happens within the Bernoulli random process approximation. I run it into a summer, I get a binomial random process. The total number of successes, k, at time t, after these 6 blocks, so n here would be 6. The x sub n is the number of successes in 6 trials. The probability that that is equal to k is n choose k times the times p to the k and times 1 minus p to the n minus k. Well, what is p? P is this probability that an arrival happened in a particular block. Well, it's going to be the same for all blocks because we've got this constant rate of arrivals, lambda arrivals per second. And what's the probability that we have an arrival in a block? Well, I'm going to give you an approximation that works when we have a really small time duration. It's going to be lambda, the number of arrivals per second, times the duration of the block. So if I have a really small block, let's say lambda is 1 arrival per second and the duration is 1/100th of a second, then it's going to be 1 times 1 over 100, and I'd have about a 1 over 100 probability of having an arrival in that block. So what is the arrival in the block? Well, the total time is t, and we have n blocks, so the duration of each block is t divided by lambda, or t divided by n, and then of course I still have the lambda over here. So when I plug in this into the binomial PMF, I get n choose k still. I have p to the k. P is lambda t divided by n to the k. And I have 1 minus p, 1 minus lambda t divided by n to the n minus k. And what I'm going to do is I'm going to say that the probability that I have k arrivals in the Poisson process is equal to the limit as n goes to infinity of this probability that xn equals k. As I said, the block gets smaller and smaller by letting n go to infinity. That probability is going to become exact. So the probability of k arrivals I'm going to rewrite as x of t for continuous time now equals k. This is the probability of k arrivals in the time from 0 to t. This is equal to this limit. Well, let's rewrite this limit. limit as n goes to infinity, and n choose k, I've got n factorial divided by k factorial and n minus k factorial. I'm going to write it like this. And then the second term is lambda t to the k power divided by n to the k, and then 1 minus lambda t over n to the n minus k. Well, let's divide these terms. Well, actually, let's write this one more time. Let's leave the limit and go to infinity, and let's write this. Take these two terms and this term and put them in the first term. Okay, so I've got n factorial divided by this. I've got n times n minus 1 times all the way down to n minus k plus 1. Okay, that's this term. And then in bottom I have n to the k. That's also k terms. It's going to be n times n. Okay, the second term now is going to be these two remaining things. Let me pick a different color here so you can see. It's going to be this term and this term. So I have lambda t to the k divided by k factorial. And then this final term, what I'm going to do is I'm going to write it as 1 minus lambda t over n to the n divided by the 1 minus lambda t to the n to the k. This would give me the n minus k. Okay, well, what are the limits of these individual terms? Well, this one is I've got an n over n times n minus 1 over n, multiply it all the way down to n minus k plus 1 over n. This limit, well, the first term is always 1. Second term is pretty close to 1, and as n goes to infinity, this is also going to be 1. The difference in the numerator doesn't matter anymore because this is constant and the n is going to infinity. So this becomes limit of n goes to infinity of 1 times all the way up to 1, and I just get 1. Okay, how about this second one? This second one is not a function of n at all. So the limit here, limit as n goes to infinity, of this term, lambda t to the k divided by k factorial, is just the same thing. It's not a function of n. Divided by k factorial. And then the last one is the one that's going to be perhaps the most obtuse. It's this top term. This top term is actually something we'd look up in a table, and we'd find out that that limit of the numerator is e to the minus lambda times t. It's 1 minus x over n to the n is e to the x, or e to the minus x. So here we have e to the minus lambda t. The numerator, the limit of the numerator, as n goes to infinity, this term gets increasingly small and just goes to 0. I've got a 1 to the k. So I've got to divide it by 1 to the k. So this one is going to be e to the minus lambda t. Okay, so putting those three together, what I've got here is that the probability that x of t is equal to k is equal to this lambda t to the k divided by k factorial, and I've got an e to the minus lambda t. We've got a 1 lambda t to the k divided by k factorial and e to the minus lambda t. So this is the probability that x of t is equal to k. And this is valid for any positive t greater than 0. And it's valid for k equal to 0, 1, 2, and any positive integer. Because it used to stop at n, but remember we let n go to infinity. So this is the PMF of the Poisson process, the probability that x of t is equal to k. That's what we had meant to prove, and that's all for this video segment.